We live in an unimaginably large universe. But what's it all made of? It may seem like most of the universe is matter. In our everyday experience, you might see how the combinations of elements compose the world around us. We breathe oxygen, there's metals all around, and life as we know it is carbon-based. Different sorts of combinations of elements, matter in short, makes up the physicality that we see here on Earth, the moon, the planets in our solar system, and the sun. However, there's much more than this. Everything that we can see makes up less than 2% of the universe's contents. Upon observing distant galaxies, we note that stars do not orbit a galaxy in the way Johannes Kepler calculated for a typical orbit. Kepler's laws say that as an orbiting body increases its distance from the center of mass, its orbital speed should decrease. However, we observe these distant stars to orbit at the same or even an increasing speed with increasing distance from the galactic center. The only solution to this is that there must be more mass that we cannot see. This unseen mass is called dark matter, first inferred by Fritz Zwicky in 1933. Dark matter does not interact via the electromagnetic force. This means we cannot see it. We can only measure it by observing its gravitational effect on nearby objects, or by observing the lensing effect it has on light. Most of the matter in our universe is dark matter.
It is also clear that light itself makes up a portion of the universe in the form of the electromagnetic spectrum. Our sun and other stars are made up of matter, but also particles called photons. This light radiation surrounding us is of various energies in the form of X-rays, infrared light, and even microwaves. Per its name, visible light is the only light that our eyes can see. Of the light that reaches us, less than 1% is in the visible spectrum. In 1964, the cosmic microwave background was discovered by Robert Wilson. The cosmic microwave background, or CMB for short, is an electromagnetic radiation that fills all space. CMB is a relic from the Big Bang. It makes up most of the light in our universe.
We have known of these two components of the universe for quite some time and have tried to understand and model the universe accordingly. In trying to model our universe, Albert Einstein attempted to use these two components to model a static one. It was a common belief at the time that our universe was static, or non-expanding. He realized while constructing this model that something was not quite right with a universe composed solely of matter and radiation. He could not construct a model universe that doesn't expand without the addition of an extra parameter. So he introduced what's known as the Cosmological Constant, a correction to the instability of a universe made of only matter and radiation. This mysterious constant allowed for a description of a static universe.
Unfortunately for Einstein, though, Edwin Hubble came along and made his famous discovery that all galaxies outside of the local group are accelerating away from us. He made this discovery after realizing that light from galaxies far away was being redshifted. Redshifted light is light that has been stretched and shifted in color. You commonly observe the same phenomena when you listen to a car speeding by. The pitch you hear goes down as the car speeds past. The main reason the light is redshifted is because the source of light is moving away from us. So the universe must be expanding. Upon Hubble making his groundbreaking discovery, Einstein tossed out his cosmological constant. This allowed for equations to describe an expanding universe. However, the cosmological constant found a new interpretation in the coming years.
Cosmologists discovered what is known as dark energy many years later, in 1998. Dark energy is an energy that permeates all space and provides an outward pressure on spacetime, forcing an acceleration of spacetime. Think of it as a force that opposes gravity. Roughly 69% of the universe's content is this dark energy, although more is unknown than is known about it. While Einstein's equations did describe a universe which expands, they did not predict the rate of expansion to increase. So the cosmological constant was eventually brought back into play, taking on a new interpretation which allowed for not only an expanding universe, but an accelerating one. We call this form of energy dark because that's what it is. We cannot directly observe it, and we really don't know what it is aside from the observable effect that it has on the expansion of the cosmos.
So why do we even care about these components then? Well, each component, matter, radiation, and the cosmological constant, contributes some amount of energy that permeates spacetime. We quantify this idea with a parameter called energy density. The energy density of our universe defines the curvature of spacetime. This curved spacetime was the vital part of Einstein's theory of general relativity. His new and improved theory of gravity, published in 1915. These energy parameters essentially tell space-time how to bend, and curved space-time, in turn, tells matter and radiation how to move. So this curvature of space-time is gravity.
The benchmark model is our current model that we use to describe the universe that we find ourselves in. Currently, the three defined properties are radiation, matter, and the cosmological constant, also known as dark energy. The cosmological constant makes up the majority of the universe, about 69%. Matter takes up another large chunk, about 31%, and radiation takes up less than 1/1000th of a percent of the universe. These three properties seem to explain what fills the universe. Having talked about dark matter, we know that we don't see most of the matter in our universe. Visible matter composes about 5% of the universe. So how much of this do we actually see? Well, it turns out 85% of matter exists as gas and dust outside of galaxies and is too low in density to be seen. Therefore, all the matter in your experience only makes up about 2% of all the matter in our universe. Try to wrap your head around that.
So, cosmology is a dynamic, ever-changing subject, and more new discoveries are being made with advancing technology. The James Webb Space Telescope, for example, set to launch in 2021, will peer further into the past than we've ever been able to before. It is basically a new and improved Hubble, allowing us to see the earliest galaxies and stars and to help us learn more about the early universe. It is a big universe with a lot to wonder about. Stay curious, my friends.